Welcome to Module 5. This might be the most important module of this entire course. We've learned how to write smart contracts. We've learned how to deploy them. But there's one thing that separates professional developers from amateurs. That's testing. Testing isn't optional. It isn't nice to have. In smart contracts, testing is insurance against catastrophic failure. By the end of this module, you'll understand why, and you'll know how to write the tests that prevent disasters. Let's begin. Let me show you the difference between traditional software and smart contracts. In Web 2 development, you deploy code to a server. A user finds a bug. Maybe the app crashes. You see the error in your logs. You fix the code and you redeploy. Downtime? Yes. Are users frustrated? Maybe. But the data is safe. The application can be patched. In smart contract development, you deploy code to the blockchain. A bug exists. Users call the contract and interact with the bug. Funds are lost forever. There is no undo button. There is no redeploy. The money is gone. In 2021, a contract called Polynetwork was exploited. A single bug, a vulnerability developers should have caught in testing, cost $611 million. That's $611 million permanently lost. That was 100% preventable with proper testing. That's the fundamental difference. In traditional software, bugs are inconvenient. In smart contracts, bugs are catastrophic. This is why we test. There's a philosophy in professional Ethereum development. If it's not tested, it's broken. This isn't cynicism, it's realism. Assume every line of code has a bug until you've proven it doesn't. Assume every edge case will be exploited. And assume every path through your code will be tested by someone trying to break it. In traditional software, we deploy. If a bug appears, we fix and redeploy. Users experience downtime but survive. In smart contracts, we deploy. The bug exists forever. Users lose money forever. No patches exist. The only solution is to test thoroughly before deployment. Test the happy path. Test the failure cases. Test edge cases. Test with random inputs. Test the contract like someone is actively trying to break it. Because someone might be. This isn't optional. Every professional Ethereum developer writes tests before deployment, aims for high code coverage, tests edge cases and failures, and runs fuzz tests to find unexpected bugs. If you skip this, you will lose money. Guaranteed. Testing is not a burden. It's protection. It's professional practice. You need to embrace it. Now let's set up. You've already seen some of this in Module 4, but let's go through it again for completeness. This one command installs Foundry. Then we run Foundry up. This installs Forge, Cast, Anvil, and Chisel. We create a new project and CD into this project. Foundry automatically initializes a Git repository, creates the directory structure, sets up a foundry.toml configuration, and generates example contracts and tests. This structure is standard. Every Ethereum project using Foundry follows this layout. The structure matters because it's professional. Everyone working in Ethereum uses this structure. Auditors expect it, and tools understand it. Follow this pattern in every project. Now we're ready to write some tests. Let's do it. Let's work with a simple example contract so you can focus on testing, not contract complexity. Here is a counter contract. The uint256 public count is a state variable that is initialized to 0. We have the increment function, which adds 1 to count, and a decrement function, which subtracts 1, but only if the count is greater than 0. This check prevents underflow, a bug where count goes negative. So what do we need to test? Well, we need to start by testing that the count is initialized at 0. Then we test that the increment function increases count by 1. We test that decrement decreases the count by 1, and decrement also reverts if the count is 0. That's our testing agenda. Let's write some tests for each. In Foundry, tests are written in Solidity, the same language as your contracts. Here, we create the file counter.t.sol inside the test folder. The .t.sol suffix is convention for test files. At the top, we import the test.sol contract from the forward standard testing library. This provides assertions like assertEq and cheatcodes accessed via vm. We import our counter contract from source counter.sol and we create our test contract. This will be called counter test and it inherits the test contract that we imported above. Next, we write our setup function. This setup function is critical. It runs before every single test. It creates a fresh, clean instance of your contract. This is why tests are isolated. One test can't affect another because each test gets a new instance. So why fresh instances? Imagine if tests shared state. Our first test would call increment. The count would be 1. Then test 2 would run without calling increment. It expects the count to be 0. It would thus fail. Shared state causes test interference. Fresh instances prevent this. The setup function is your foundation. You need to master it. Now let's write some actual tests. First, we test the contract's initial state. Here our test name is test initial value is 0. This test name is crucial. It says exactly what we're testing, that the initial value is 0. Next we have an assert function. This assert equal counter.count, 0 asserts equality. If counter.count is equal to 0, the test passes. If not, it fails. The second test is a test for increment. Here, we call the increment function and assert that count is now 1. It's simple, but essential. Notice the naming, test, followed by what the test is doing. Any function starting with test is automatically discovered and executed by Foundry. The name describes what is being tested. Good test names make debugging easy. If test decrement reverts when 0 fails, you immediately know what's broken. Foundry provides many assertions. There is assert equal, assert not equal, assert true, assert false, assert greater than, and assert less than, along with many others. Happy path tests are necessary but insufficient. You must also test failure cases. Let me show you exactly what happens when you run a test. First, Foundry calls your setup function. It deploys a fresh counter contract. The contract state is initialized. Then, a new instance of counter is created with count equals 0. This instance is isolated, no state from previous tests. Then your test function executes. In test increment, we call increment. We check the result, assert equal counter.count is 1. If it's true, the test passes. If it's false, the test fails. After the test finishes, that instance is discarded. The next test gets a fresh instance. This isolation is critical. Every test is independent. Tests can run in any order and results are consistent. This is what makes testing reliable. Testing success is not enough. You must test failure as well. This is where many developers fail. Beginners write tests that only check, does this function work? Professionals also test, does this function fail correctly when it should? Here's the test. Function, test decrement reverts when 0. The vm.expectRevert function is a cheat code. It tells Foundry the next call should revert with the message underflow. If it doesn't revert, the test fails. If it reverts with a different message, the test fails. Counter.decrement is the function we call and expect to revert. When this test runs, setup deploys a fresh counter with count equals 0. vm.expectRevert sets an exception. Counter.decrement is called. The required check fails because count greater than 0 is false. The contract reverts with underflow. The test compares the expected message with the actual message. They match and the test passes. If decrement didn't revert or reverted with a different message, the test would fail. This test ensures your error handling works correctly. If someone calls decrement when count is 0, they should get a clear error message, not an unexpected crash. VM is an object containing cheat codes, special functions for testing. vm.expectRevert is just one. There are many more. vm.prank, vm.deal, vm.warp, and vm.snapshot are just a few. These are incredibly powerful for testing. Now we test multi-user scenarios. Many contracts have permission checks. Only the owner can call certain functions. Only admins can pause contracts. How do you test this? In your test contract, message.sender is always the test contract itself. How do you simulate a different user? The solution is to use vm.prank. The vm.prank open brackets address 1 tells Foundry that the next call is going to be from address 1 and not from address this, the calling contract. So when we call owner.restricted, the contract sees message.sender is address 1. The required check inside restricted fails because address 1 is not the owner. The transaction reverts with not owner. The test passes because we expected this revert. This test verifies that access control works, unauthorized callers are rejected, and error message is clear. If you need to call multiple functions from different addresses, we can use the vm.prank function with different addresses passed as an argument. Access control is fundamental to smart contract security. If your permission checks are wrong, funds can be stolen. Testing access control is non-negotiable. vm.prank is one of your most powerful testing tools. Use it liberally. Now we actually run the tests. We use the command /test to run our entire suite. This finds all tests in the tests folder. It compiles them and runs every function starting with test and reports the results. We can also run specific tests by using the --match test command. We can also see how much gas each function uses with the /test --gas report flag. This helps optimize. If a function uses unexpectedly high gas, we can investigate. To see more details of a test, we can increase the verbosity by adding the -v flag. /test is your constant companion. Run it, fix failures, and repeat. So far, we've written tests with specific inputs. But what if there's a bug that only appears with certain edge cases? What if there's an overflow bug at max uint 256? What if there's an off by 1 error at a specific value? You can't manually test all possibilities. Fuzz testing is automated random testing. Instead of you choosing inputs, Foundry generates thousands of random inputs automatically. For each input, it runs a test and checks if it passes. If any input causes a failure, Foundry reports it. If we look at this fuzz test, notice the parameter uint256 amount. Foundry will call this test with many random values. For each value, it asserts the transfer works correctly. We can use the vm.assume cheat code to filter out invalid inputs. If any fail, Foundry reports which input caused the failure, and this helps to debug. Fuzzing finds integer overflow or underflow bugs, off by 1 errors, logic bugs at boundaries, and unexpected reverts, bugs that manual testing would miss. If you write only one fuzz test, you'll find bugs you didn't know existed. Professional developers include fuzz tests in every serious contract. It's not optional, it's expected. You can't manually test thousands of inputs. It's impossible. Only automation can do this. Fuzzing is how you find bugs before users find them. Fuzz testing isn't advanced, it's essential. Start using it now. Let me share the patterns that professional developers follow. You need to follow these principles. 1 assertion per concept. Don't test multiple things in one test. Why? If a test fails, you immediately know which concept broke. You need to have a setup function because this allows every test to have a clean slate. And you need to have descriptive test names. You need to say exactly what you're testing. Aim for high coverage. You need to test the happy path, the normal flow where transfer succeeds and withdrawal succeeds. You need to test failure cases, invalid inputs, unauthorized callers, and insufficient balance checks. You need to test your edge cases or boundary values. zero values, maximum values, and boundary transitions. Access control verification. Check that only the authorized callers succeed. You should target 80% code coverage as a minimum. Every important line needs to be tested. You can use forge coverage to measure your test coverage. The output will show which lines are tested and which aren't. If a line isn't tested, either it's dead code or you need more tests. Professional testing is systematic. Structure, coverage goals, metrics. Follow them. Let me show you the mistakes beginners make so you can avoid them. Mistake number 1. Forgetting your setup function. Without a setup function, your contract instance isn't created. Tests will fail mysteriously. You need to always include it. If you're only testing success cases, you're missing failure scenarios. You need to test that failures fail as expected. Good names make debugging easy. Bad names hide problems. Avoid these mistakes and your tests will be solid. To recap, you understand why testing is critical. In smart contracts, bugs are permanent. Testing prevents catastrophic failure. You can write unit tests in Solidity using Foundry. You know how to use assertions such as assertEq and assertTrue. You can test failure cases with vm.expectRevert, and you can simulate different users with vm.prank. You understand fuzz testing basics that lets Foundry generate thousands of random inputs automatically. You can structure tests professionally in fresh instances, clear names, and high coverage. Every contract you write must be tested, not optionally, mandatorily. Before deployment, 80% plus code coverage, happy path tested, failures tested, edge cases tested, and access control should be verified. Please remember this. If it's not tested, it's broken. Don't deploy untested code. Ever. Now you have the skills to write robust contracts and test them professionally. In Module 6, we'll explore advanced testing patterns, invariant testing, property-based testing, and fork testing. But you have the foundation. Great work completing Module 5. You're now equipped to build secure smart contracts. The testing discipline you've learned here will serve you throughout your career.